In this video, we'll discuss about the analysis of series circuit, voltage division rule, and some worked examples. So first, we'll discuss the series circuit. A series circuit is one in which various elements like resistors, inductors, or capacitors are interconnected one after the other. So let us consider a resistor over here, R1. So resistor comprises of two ends. Okay. So one end of the resistor is connected to another resistor, say R2. So here only one end of each resistors are connected. Okay. So the other ends of these two resistors are connected to some other elements. Here let us consider VDC, a DC voltage source. So positive terminal of the source is connected to R1 and negative terminal is connected to R2. Okay. So only one end of the resistors are connected. Hence this connection is also called as end-to-end connection or cascade connection. So whenever we apply a voltage across a circuit, the current will start flowing. So the current should always be represented to be flowing from positive terminal of the supply voltage. So it will start flowing from positive terminal. It will flow through the resistors R1 and R2 and completes its path through the negative terminal. So here the current has only one path to flow. So the current will remain the same. So the same current will flow through each resistor. Okay. So in the case of a series circuit, the current will remain the same or constant. So now let us consider this series circuit. So here three resistors R1, R2 and R3 are connected in series. VDC is the DC supply voltage. So this voltage gets divided into VR1, VR2 and VR3 and the current will start flowing through the circuit. So this is IDC which will remain constant. So now we'll apply the Kirchhoff's voltage law in the above circuit. So we can write VDC is equal to VR1 plus VR2 plus VR3. Let this be equation number 1. Again by using Ohm's law we can write VR1 is equal to IDC into R1. Here IDC is the current flowing through all the resistors. So it will remain the same. So now let this be equation number 2. Similarly, we can write VR2 and VR3. Now VR2 is equal to IDC into R2 and similarly VR3 is equal to IDC into R3. So next we'll substitute equation number 2, 3 and 4 in equation 1. We'll get VDC is equal to IDC into R1. So in place of VR1 we are substituting IDC into R1. In place of VR2 we are substituting IDC into R2. And similarly in place of VR3 we are substituting IDC into R3. So here IDC remains constant, so we will take it outside and the remaining terms are R1 plus R2 plus R3. So this R1 plus R2 plus R3 is nothing but R suffix T, which is the total resistance or equivalent resistance of this particular series circuit. So the total resistance RT is given by sum of all the three resistors R1, R2 and R3. So in other words, it can be stated that the total resistance or equivalent resistance of a series circuit is given by the arithmetic sum of the resistors connected together in series. Say for example, if n number of resistors are connected in series, then the total or the equivalent resistance is given by sum of all the resistors, say R1 plus R2 plus R3 and so on up to R suffix n. So these are some of the important points to be noted. First one, as I said earlier, the current will remain the same in the case of a series circuit. The voltage will divide. VDC is equal to VR1 plus VR2 plus VR3 and so on up to VRN. And the total or the equivalent resistance is given by the arithmetic sum of all the individual resistors connected in series. And the total resistance will always be more than the individual resistances. That is, RT is more than R1 as well as RT is more than R2 and so on. So next we'll discuss about the voltage division rule. So in the case of a series circuit, as we have already discussed, the voltage divides, current remains the same. So now IDC is the total current flowing through the circuit. The equivalent resistance already we have found out. RT is equal to R1 plus R2 plus R3. Now we can write the total current is equal to total voltage divided by the total resistance. This is given by the Ohm's law. Okay. So IDC is the total current, VDC is the total supply voltage, and RT is the total resistance. So now by applying Ohm's law here, we can write VR1 is equal to IDC into R1. So from equation number 8, IDC can be written as VDC divided by RT into R1. So this can be rewritten as VDC into R1 divided by R1 plus R2 plus R3. So this is the voltage division rule. Now if you want to find out the voltage drop across any of the resistors, provided the supply voltage, then we can write it as total voltage multiplied by the same value of resistor divided by sum of all the resistors connected in series. Okay. In a similar way, we can write VR2 also. So now VR2 is given by IDC into R2. So IDC can be written as VDC by RT multiplied by R2. VDC into R2 divided by R1 plus R2 plus R3. So if you see here also, VR2 is given by total voltage multiplied by same value of resistor divided by sum of all the resistors connected in series. So and VR3 is given by total voltage multiplied by same value of resistor, that is R3, divided by sum of all the resistors. Okay. So next we will discuss some worked examples. So this is a given circuit. So here we have to find out the voltage. So what is the voltage VAB across the resistor shown in the figure? So we have to find out the voltage across this particular resistor. Okay, 50 ohms. So this 10 ohm, 50 ohm and again 50 ohm. These three resistors are connected in series and this is the supply voltage 10 volts. So now let R1 is equal to 10 ohms, R2 is equal to 50 ohms and R3 is equal to 50 ohms again. So these three are the resistors. So next we'll write the supply voltage VDC is equal to 10 volts. So now we apply the voltage division rule to find out VR3. So already we know VR3 is given by the total voltage VDC multiplied by the resistance R3 itself divided by sum of all the three resistors. Okay. So we know all the values and we can directly substitute in the above formula. So VDC is 10, R3 is 50 divided by 10 plus 50 plus 50. Okay. So this will be 500 divided by 110. On simplification, we will get VAB is equal to VR3, that is equal to 4.5454 volts. Okay. So next we'll solve another problem. So here the question is determine the total amount of power in the series circuit shown in figure 2. Okay. So again in series circuit, the current remains the same, voltage divides and at the same time power also divides. So let us solve this problem. So now we'll consider all these four resistors. Okay, R1, R2, R3 and R4. So R1 5 ohms, R2 2, R3 1 and R4 again 2 ohms. Okay, so VDC is equal to 50. So now we can find the total resistance RT. Okay, R1 plus R2 plus R3 plus R4. So by adding all these resistors 5 plus 2 plus 1 plus 2 we will get 10 ohms. Okay, this is the total or equivalent resistance of this particular series circuit. Now the total power is given by VDC square divided by RT. Okay, so VDC square is 50 square divided by 10. So 2500 divided by 10, 250 watts. Okay, let this be equation number 1. So this is the required power, but as I said, in a series circuit the power divides up. Okay, so we will find out the power dissipated in each resistor and we will add and check whether it amounts to 250 watts. Okay, so first we'll find out the total current IDC. So total current is total voltage divided by total resistance. Here the total voltage is 50, total resistance is 10. So 50 by 10 is equal to 5 ampere. Okay. So next the power dissipated in the resistor R1, that is P1 is given by IDC square into R1. Okay, this is I square R formula for finding out the power dissipated in the resistors. Okay. So by substituting the values, we'll get 5 square into 5. R1 is 5 ohms. So this will be 125 watts. Okay. Similarly, power dissipated in R2, that is P2 is equal to ID square into R2. In series circuit, current will remain the same, IDC. So this is again 5 square into 2, that is 50 watts. Okay. So next we have to find the power dissipated in R3, that is P3, IDC square into R3. So IDC is 5, R3 value is 1. So 5 square into 1 is equal to 25. And similarly, power dissipated in R4, P4, IDC square into R4, 5 square into 2, 50 watts. So now we will add all these power dissipated, P1 plus P2 plus P3 plus P4. So there will be 125 plus 50 plus 25 plus 50, that will be 250 watts. So this is equation number 2. So already we have found that from equation number 1 and 2, both the power are same. So in a series circuit, the power also divides.